Hi, I'm Mitch Gitman. I'm recreating a talk I gave a few months ago for the Seattle Cassandra Users group, Getting to a No Compromises Cassandra Right Path. Last year at Cassandra Day Seattle, I gave a talk on managing Cassandra schema migrations. I'm a senior software engineer at a company, Gridpoint. In the likely case you haven't heard of my employer, Gridpoint, it's an energy management company that offers a comprehensive IoT-based solution for enterprises, primarily retail. Gridpoint is headquartered in Reston, Virginia, with a development presence in Seattle. We've been transitioning from Postgres to a combination of Postgres and Cassandra for integration with Kafka and Spark, and we also have some SQL Server thrown in the mix. This next slide, don't ask, you had to be there. The time series schema we came up with, one of the paradigms you try to embrace with a post-SQL data store like Cassandra is to store data in a denormalized way, where you're storing the same piece of data in different tables for different queries. Our time series schema is highly denormalized. We have what we call cumulative tables that store the time series in ascending order, and then we have what we call latest tables that store the data in descending order to facilitate queries for the latest data. And on top of that, we break up the latest tables by time bucket. So, to oversimplify, where there's one cumulative table with 10 time-bucketed partitions, there are 10 completely different latest tables. And then on top of that, the time series data we're measuring is for intervals like 1 minute or 15 minutes, where the data is already aggregated over that time window, and we're not sure yet whether having separate tables for different intervals or having a single table for all interval lengths better supports our call patterns. So at this time, we're writing to both variations. So take what we're already doing and multiply by 2. We're actually writing the same measurement 4 times. Plus, we're writing to a few other tracking or audit tables that are geared towards certain other lookups. I'm really going to be focusing on the DataStax Java Driver, what's now the mainstream prevalent JVM-based client-side driver for Cassandra. And I'm going to be talking mainly about working directly with the DataStax Java Driver and its APIs rather than working indirectly through libraries that work on top of the DataStax Java Driver. Now, some engineers might say that if you're working directly with the DataStax Java Driver, you're working at too low a level to begin with. There are some obvious cases where I'd go right along with this observation, such as if you're working with Spark and you want to persist the RDDs or data frames, then you might as well just use the Spark Cassandra connector. I'll touch on those higher level APIs later. Earlier this year, DataStax released a version 3.0 of the Java driver. It now fully supports version 4 of the native protocol, which is applicable if you're on Cassandra 2.2 or 3.x. For one thing, that allows unset values in bound statements, so you're not inadvertently writing null column values. For me, what's more immediately useful about the new driver are custom codecs. From the blog post announcing the 3.0 driver, quote, in short, where before the driver had a hard-coded set of mappings between CQL types and Java types, now it has a fully dynamic, pluggable, and customizable mechanism of handling CQL to Java conversions, end quote. And for me, what's especially useful are the prefab optional custom codecs in the Cassandra Driver Extras library. For example, there's a codec for the Java Time Instant class that was introduced with Java 8 and which is immutable and works similarly to Java Times Instant Type, which has its own custom codec too. From my standpoint, I wanted to pass around instant objects, but then I'd have to convert them to the old Java util date type to insert data. Now I can use instant straight through. And then we have some retry policy enhancements with the 3.0 driver. I'll get into that later. Here we see a set of synchronous calls to session execute, one after the other with no parallelism. See, the Cassandra binary protocol, the native protocol, which is built on top of TCP, is asynchronous. The Java driver uses the Netty networking library to establish a persistent connection using the native protocol over TCP. Because the protocol is asynchronous, a single TCP connection can handle multiple requests simultaneously. Not only is the Cassandra Java client implemented using Netty, the Cassandra database server's communication with clients is implemented using Netty. With a denormalized write path like ours, where we want to write to multiple tables and none of the writes are conditional on the other ones, it's obvious we're using a sort of scatter and gather execution pattern, albeit on a single client host with multiple cores rather than multiple hosts. So it's obvious we want to call an async API for a call pattern that can support multiple simultaneous queries. But that's just this one write call pattern that can obviously be async. What about other write calls where you're only writing to one table? What about this write call coexisting with other write calls? Or other read calls where the read semantics tend to be more synchronous and the caller can afford to sit and wait for a response and doesn't benefit from sending out multiple requests at a time? Do we still need to care about going async to address these call patterns? The answer is yes. The bigger problem with calling the synchronous session execute is that when a query is executed synchronously, it ties up an entire connection provided by the connection pool. From the DataStax Java Driver documentation on connection pooling, quote, "For each session, there is one connection pool per connected host," end quote. So if the connection pool is providing a maximum of 10 connections per host, then you immediately max out at 10 synchronous queries. But suppose we go async. Thanks to the driver's use of Netty channels under the covers, a single client connection to a host in the local data center can support up to 32,768 in-flight requests simultaneously if all the queries are executed asynchronously and if you max out that config. But on a synchronous query, instead of 32,768, a single in-flight request now ties up the entire connection. One is not as good as 32,768, or 10 for 10 connections in a connection pool is not as good as 327,680. Disclaimer, just because your client can send out 32K or 327K requests simultaneously doesn't mean you'd want it to. If you do this, you're apt to overload the Cassandra cluster unless it's huge. These next few slides should be a bit of a review, so I want to crank through them quickly. I think of asynchronous queries with the session execute async method as the building blocks for writing to a denormalized schema. The execute async method returns a result set future type that's specific to the DataStax Java Driver API, but which is really just a wrapper around a Guava listenable future typed to a DataStax Java Driver result set. Now you see the earlier set of queries getting executed asynchronously as they should be. Once you have a feature in hand, what do you do with it? You don't want to just sit and wait on it and pull for when it's complete. That's defeating the whole purpose of going async. Well, the simplest thing to do is to introduce a callback, and the Guava interface for callbacks is future callback. In the ideal simple case, you have a number of insert queries going out asynchronously to write to the various denormalized tables, and none of these queries have any dependencies on each other. This is what you really want to strive for if your domain allows it. So rather than having to create a callback for every feature, we can take advantage of another feature of Guava and create a single callback for all the features combined. Here we're able to call futures all as list to take a list of features and create a single feature for all of them. And then we can call futures add callback to associate this composite feature with our own type, composite future callback. If necessary, you can be chaining and composing futures. Future callback has two methods, one success and one failure. Here we see how our composite future callback has implemented those methods. In the ideal simple case that you should be striving for, where the various inserts have no dependencies on each other, it should suffice for the single composite callback to be the destination for the right workflow. Once the callback is called, you know the workflow is complete. Unfortunately, our workflow is more complicated than that for reasons I'll touch on later, so we have to do a little extra work to determine when the workflow is complete. You'll notice a couple references to an ingestion state object here. You see, I've written our Cassandra client to be as stateless as possible. The worker classes are stateless, The DTOs that represent the incoming and outgoing data are all immutable, but I do make some limited isolated use of state. These are two things I've called ingestion state and completion state. There's not really a sharp distinction between the two kinds of state. Different ingestion states feed into completion states. Potentially different completion states feed into a root completion state. For better or worse, these states act as gatekeepers over parts of the execution. But even if they weren't doing that, they're capturing all sorts of useful information. Did the workflow succeed or fail? If it failed, what's the throwable? How long did a query take? Did a conditional query have to be executed? How long did a certain group of queries take versus another group of queries? What was the average query time for this category? What was the max? How long did the entire unit of work take? The premise here is that our Cassandra write implementation is contained in its own component. It has its own build system project and IDE project. It exposes an API that is agnostic of Cassandra if it is indeed even being passively called from outside where an API is needed. The entire Cassandra write implementation is encapsulated behind the API. The API is exposing one or more component level logical writes, each with its own method. The method and its inputs comprise the unit of work. What's important about our keyspaces schema is essentially its idempotent. Our write unit of work doesn't have to be all or nothing. It doesn't have to work like a single ACID transaction where if the entire write doesn't succeed, then the entire write fails. It's essentially a write at least once contract, and then we can filter out the duplicates. For this component, I can think of 4 contracts for how this component interacts with the rest of an application. The important thing is that all these interfaces are fronting an inherently asynchronous implementation. With our highly denormalized schema, we want to be writing to multiple tables, and we want to be sending out those write requests independent of each other. And this is where it's so useful for the schema to be idempotent. If an insert into one table in a write unit of work succeeds, but the rest of the inserts fail, it's not a big deal. There's nothing to undo. You can just retry and accept the duplicate. I'm listing these choices in a sort of rough evolutionary order. I'll explain each of these contracts in detail, but for now I can say that fire and forget is the most simple and naive contract. Although it's not necessarily wrong, it's perfectly acceptable in certain use cases. Streaming consumer is the most mature contract, but I want to spell out these choices here just to make it clear that we have choices. What do these 4 contracts have in common? They all call session execute async to asynchronously process the results. They all produce a single result. Think of a map-reduce workflow. All the asynchronous queries that have been chained and composed have to see their individual callbacks called, whether it's on success or on failure. Either that or they time out collectively. Only if all the queries callbacks succeed does the entire write succeed. If any of the queries callbacks fails or times out, the entire write fails. And they all produce metrics, not intended to be propagated to the caller though. First, we have fire and forget. Its hallmarks: it provides a passive API to consumers. This contract is still asynchronously processing the results, still handling failures, just not holding up the main caller thread to do so. The caller gets no direct feedback on the fate of the write. Some considerations for fire and forget. What if the write fails? The caller doesn't get any immediate feedback that the write failed. The caller is already long gone. So, what is fire and forget good for? One thing is logs and logging-like data for when the caller doesn't care that the write fails. When a failure to write to Cassandra is not a failure from the standpoint of the consumer. You can live with some missing logs until the issue is rectified. Next, we have block on callbacks. Its hallmarks: it too provides a passive API. You're wrapping a synchronous contract around an asynchronous interaction, so it holds up the main caller thread for the callbacks to come back. Because the caller is waiting for the Cassandra write to complete, it's at the mercy of any driver timeouts. Theoretically, it could wait forever. So it's important with this blocking contract to give the entire write a timeout. And then you can configure the timeout and vary it based on how big a write it is. Presumably, you'd be throwing an exception on a timeout just as you'd be throwing an exception on a failure, so the caller is forced to decide whether to retry. Considerations. Scalability is limited by the synchronous caller thread. The thread is just sitting there idle throughout the async workflow. It's not being reused somewhere else, and a thread in the JVM takes up a significant amount of memory. By the same token, this force blocking provides a sort of poor man's throttling mechanism. The Cassandra clients are always blocking on the completion of the unit of work for a write, although even then the clients can get out ahead of the Cassandra cluster. So we see what blocking callbacks is good for. What you see here is a rudimentary mechanism to wrap a synchronous contract around Cassandra's asynchronous workflow. There's nothing Cassandra specific about what you're seeing here. The real work of the Cassandra write is being placed in a runnable and submitted through an executor service from Java Util Concurrent. There is a pair of countdown latches from Java Util Concurrent, and the second countdown latch, the one named done signal, is waiting for the entire asynchronous workflow to complete. This is where the timeout is necessary, and notice the method getWriteTimeout seconds. That timeout varies depending on whether the call is writing a single measurement, a single logical row, or multiple measurements. But the important thing to keep in mind here is that all the future callback on success and on failure calls for all the execute async calls going out to Cassandra are eventually resolving back to a single resolution that can either succeed or fail and either complete or time out. So the fact that we have a single done signal await call means that somewhere else the completion of the entire asynchronous workflow can be recognized by a single done signal countdown call. Next we have return a future semantics. Let me explain. Because all the future callback on success and on failure calls for all the execute async calls going out to Cassandra are eventually resolving back to a single resolution that can either succeed or fail, complete or time out, the persistence component can represent that single resolution as a future and return it to the caller. The trick here is to return a single future synchronously without waiting for any server interactions, and that might require chaining features in the implementation where you're distinguishing between sort of the airplane's wait on the runway from the airplane's time in flight. So what are its hallmarks? In these first two respects, this works the same way as fire and forget. Now the caller is responsible for handling timeouts. The caller has more control over the rate at which it calls the write component. The caller has to check the future as to whether the write failed apart from a timeout and it needs to retry. Compared to blocking callbacks, you're putting a lot more responsibility to the caller. Considerations. So this opens up the ability to handle a greater workload, but this means you're trusting the caller not to overload the Cassandra cluster. How does the caller know? How does the client using the Cassandra client driver, the Cassandra application code itself know? I'll get into that next, but for now, suffice it to say that this can mean exposing some of what the driver is doing to the caller, which violates the encapsulation of Cassandra within the write component. So what is return a future good for? It can be good at internally managing throttling. Once you break the chains of supporting a synchronous contract, if the caller is noticing the Cassandra component's responsiveness lagging, it can queue up the units of work representing the discrete write API calls. My sense is this can get pretty complicated pretty fast if you try to implement this workflow yourself. Also, tapping into a streaming or workflow solution. What I mean by this is that the caller is being managed by some streaming system, and once the future is in the hands of the caller, it knows how to link it into the streaming system. If this works, the benefit is that all this can be accomplished without the Cassandra write component having any dependency on the streaming mechanism being used. And finally, we have streaming consumer semantics. This is potentially where you want to get to eventually, at least in a near real-time use case. Now the write component notifies upstream producers when it's available or unavailable. It's active rather than passive. It can signal back pressure. It has the ability to elastically respond to load, so it gives a way to maximize throughput and scalability based on the responsiveness of the Cassandra cluster. And then there's the question of whether we're making our custom write component a streaming consumer or we're letting the streaming toolkit write directly to Cassandra. Throughout this discussion so far, we've been talking about calling the DataStax Java Driver directly rather than about calling a higher level API. Later on, I'll talk a little bit about higher level APIs, but when it comes to tapping into a streaming mechanism, it gets confusing if you don't make that distinction. What I would like to do is take our own low-level Cassandra write component and plug it into a streaming workflow. However, I can't stand here and show you, hey, here's how we're writing our own streaming consumer, even though this is the thing I'm most interested in. The goal would be to still have our own custom write implementation, but we would be able to leverage a third-party streaming provider. So the streaming consumer contract is a natural fit with a Kafka producer for near real-time streaming applications, and it has the potential to plug into different streaming providers. This goes back to our goal of leveraging a third-party streaming provider. Perhaps you want to work with a library that implements the reactive stream specification. Perhaps you want to integrate your Cassandra write component with the new Kafka Streams library. Kafka Streams ties back to the preceding use case where the application is reading from Kafka and writing to Cassandra. So this brings me to a set of questions that are worth asking when deciding between these semantic contracts. You may very well find that your existing usage patterns are not necessarily as scalable as other usage patterns, but maybe they're scalable enough for now. So back to the original question, you may very well find yourself wanting to support more than one contract and to go back and forth between these choices, such as through configuration. So we could view this question as a multiple choice question. In our case, the initial prototype was fire and forget. Then we introduced block and callbacks to support our existing contract. Inevitably, we want to introduce a streaming consumer. But even if we get to the point where we only need a streaming consumer in the field, I'd anticipate that we'd still want to preserve some integration tests that use at least some of the other contracts, if only because that might better isolate the right implementation from the way it's being consumed. I asked the question earlier, how does the Cassandra write component know to keep from overloading the Cassandra cluster? In general, I can think of some techniques for avoiding overloading a Cassandra cluster or any set of servers that range from the less sophisticated to more sophisticated, from stress testing a production-like environment to elastic provisioning and deprovisioning. If the Cassandra client is noticing the server-side's responsiveness lagging, it could queue up the units of work representing the discrete write API calls. It would be better if you could take this feedback and let it be an input to a streaming provider. At this point, you may be thinking there's something else the client could be doing. You may be asking, but what about throttling? Or I would subtitle this slide, how to avoid thread.sleep without getting ahead of yourself. I should note that nowhere in our main code are we calling thread.sleep. This is the point where I wish I could say I had a nice, easy solution I could share with you. One possible way to think about our write path is that it takes, well, as long as it takes. If the cluster is overloaded, it just takes longer, and as long as it doesn't time out, it's okay. Unfortunately, with Cassandra, this is the wrong way of thinking. A couple of considerations. Just because the client has gotten a response from the coordinator node on the Cassandra cluster that the write is completed at the expected consistency level doesn't still mean that the write hasn't incurred some persistence debt on the cluster that wasn't there before. The mem tables in memory still need to be flushed to SS tables. The SS tables still need to be compacted. Theoretically, a client, like for a bulk import, could be pumping out writes at a rate faster than the cluster can keep up with, and the cluster just keeps falling further and further behind. Beyond that, our client-side write component doesn't control how often it's getting called. It could try to keep track of how many in-flight calls there are and queue them up, or literally throttle the individual calls, or start rejecting them over a certain threshold. A more sophisticated approach would be to call the getState method on the client session object and check the stats provided there, like number of open connections and number of active requests. And this is where I would recommend going back to the connection pooling page in the driver manual. Ultimately, there should be ways for the writer to signal back pressure upstream. For us, this is very much TBD, but for us, this is something where the state we're tracking, ingestion state and completion state, could serve as an input. Beyond the timeouts that constitute a functional failure, which we already have in place, a negative trend with our internal metrics, or just one slow completion state would be enough to signal upstream, hey, hold off. I'm adding this item at the bottom here based on feedback I received post-talk. Remember how I was talking about how the primary reason you should be calling session execute async rather than its synchronous counterpart is that the synchronous API ties up an entire connection, whereas the async API can support up to 32K in-flight requests simultaneously to a single host in the local data center if all the queries are executed asynchronously and if you max out that config. And not that you would want to max out the config because you could overload the cluster. That config is this: the set max request per connection method on the pooling options class that's used to initialize the driver client. If setting that to a high value threatens to overload the cluster, then conversely, setting it to a low value is a nice, simple, tunable way to throttle the load that that client is bringing to bear on the cluster. The default for a local distance host is 1024 requests per connection, so you'd be explicitly setting it to an even lower value. In subsequent efforts tuning a Cassandra client and a cluster to try to keep the former from overloading the latter, I found that pooling options set max requests per connection is best tuned in tandem with two server-side configurations in Cassandra YAML: native transport max concurrent connections and native transport max concurrent connections per IP. Even then, you want to be checking a monitoring tool like DataStax Ops Center that's picking up the JMX metrics coming from Cassandra to see if you're bumping up against those limits during a load test. In its current incarnation, our write component doesn't manage retries. It defers to the outside caller. It trusts the caller to retry and to not retry immediately. But there are opportunities to customize retries with the Cassandra client, if only to give more information to the caller. The way to customize retries is with the retry policy that you can configure the driver with. Here I'm showing the sample configuration from the driver manual's page on retries. So my general view with configurations like retry policy is trust the default configuration. Don't go custom configuring it unless you know what you're doing and know what you want to do. But I do want to point out some enhancements to retry policy with the new 3.0 version of the driver. There's a new idempotence aware retry policy that you can decorate any retry policy with. But beyond that, retry policy offers this new method, on request error. You see the driver exception argument there? One of the new driver exception types that were introduced with this change is overloaded exception. Quote, indicates that the contacted host reported itself being overloaded, end quote. Potentially, this is a place where you could introduce some kind of back off or queue any subsequent write requests. The important thing, however, is to avoid getting in a vicious cycle where the clusters being overloaded causes even more requests to go out. And so the clusters being overloaded cause it to get even more overloaded. And this goes back to the Cassandra write components contract with the rest of the server-side application that it's part of. A well-established technique with web services and messaging systems and logging is to introduce a correlation ID so you can tie together different messages and rows to a single event. And often this is done using a UUID, a universally unique identifier that looks like an example there. CQL offers two UUID types, UUID and time UUID. Time UUID is what's called a version 1 UUID, so it's time-based. And here's the nice thing about time UUID. From the CQL documentation, quote, a version 1 UUID includes the time of its generation and are sorted by timestamp, making them ideal for use in applications requiring conflict-free timestamps, end quote. We've had success making a time UUID column the least significant part of the clustering key, so it acts as the version on what would otherwise be conflicting entries on the same row or updates on the same row. The DataStax Java Driver has a UUIDs class that, among other things, lets you generate a version 1 UUID that can then be persisted as a time UUID. On the server side, there's a similar facility, the built-in now function that gets executed on the coordinator code. So what's the difference between generating a time UUID on the client side and generating it on the server side? If the coordinator node generates a time UUID, it's only good for that insert. If you generate it on the client, the UUID can be applied to all the insert calls across the entire logical write. It really can work as a correlation ID. So this works for everything in the scope of the Cassandra write component, but what if your Cassandra writes are being fed by Kafka reads? The messages in Kafka really ought to be getting saved with their own correlation ID, which in turn traces back to some originating user event. You want to correlate the rows in Cassandra to the originating user event, so almost inevitably you're going to be wanting to save an incoming UUID, whether in addition to or instead of any UUI generated within the Cassandra client. And just to state the obvious, not only should you be writing these UUIDs out to the Cassandra tables, you should be incorporating them into log messages. With our Cassandra schema, we religiously adhere to an append-only model, no deletes, no updates. We do have a few tables where we have to do a conditional write, only write a value if it doesn't match the last value read in. This leads to the following execution sequence. First read, then, depending on what value, if any, was read, possibly write. Guava adds a nice interface to support the conditional chaining of futures async function, and it has a single method apply. Here's a truncated version of one of our async functions. And here's how it's composed into a chain of futures where the chain is collapsed into a single future. Technically, there's the possibility for the read to miss a write that was happening effectively at the same time, and for the write for that read to happen on top of the write already happening. This is unlikely to happen for us, but even if it did happen, it's okay. The model is effectively idempotent. We can handle a redundant write. The subsequent read will filter out the duplicate. Now, what if your schema is not effectively idempotent, or you just don't want the clutter of the redundant rows getting in there in the first place? And what about the read before write making for a somewhat complicated asynchronous execution flow, what with having to chain the conditional write on the read using async function? We could make this a lot simpler if we could collapse this into a single query. This is where the if keyword comes into play. And the moment you introduce the if keyword, you're doing a more expensive coordinated operation than a simple statement. You're entering the world of lightweight transactions, or CAS, compare and set, which was introduced in Cassandra 2.0. But there's one more missing piece that's not so obvious, and that's the fact that that read is potentially having to go out to disk every time. So whether you're doing a separate read and write or a conditional transactional write, that one read could be making the conditional table write the laggard among all the async writes that go out. So what we've done, if only for the sake of the write path, not the read path, is to introduce caching. We've modified the table to cache just the last row in the table, where we're storing all the rows in descending order. Now these reads never have to go out to disk, and this is a relatively small table in our schema, so its memory usage is minimal. Another addendum: when I first gave this talk, I referred to lightweight transactions as a better approach than doing a discrete read then write, but really it depends. Doing the read before the write avoids the extra contention of the transaction coordination. So if speed is of the essence and you're okay with the extra code complexity and you can tolerate duplicate writes where two clients are reading the same state unaware of each other, or if you won't run into that situation in your use case, then breaking up the select query and the conditional insert query with an async function approach is preferable. At least the caching mitigates the performance cost either way. Okay, this is not specific to writes, but I'll get to where this becomes useful for writes. To avoid the so-called wide partitions problem, we've introduced a bucketing scheme. Buckets are agnostic of calendar or year or month or day, just time window from one timestamp of milliseconds from the epoch to another timestamp of milliseconds from the epoch. How wide you make that window is a matter of configuration. Ultimately, what you get is a number. For our so-called cumulative tables, the bucket number becomes a qualifier in the partition key. For our so-called latest tables, the bucket becomes a qualifier in the table definition, the table name itself. And then we have a bucket type that's reused across writes and reads. Here are some highlights. And then we have a mapper between timestamps and buckets. Here's the mapper interface. Now we're starting to get into where the bucketing scheme becomes especially useful for writes. What you see here is a graphic from a DataStax webinar from last year, Avoiding Anti-Patterns, How to Stay in Love with Cassandra. It's supposed to show how, if you're not careful, using the batch keyword to group multiple insert statements together can be far worse than executing all inserts independently. Let me show you the graphic where all the inserts are done independently without batching, provided you're using the token aware policy on the driver as you should be. Here it is. But now there is a use case where batching is a good thing that justifies its existence, and that's where you're ensured that all the rows you're inserting are in the same partition. This way, if your replication factor is 3, you're going to be writing to 3 nodes with a single batch statement regardless of how many rows you're inserting. And this fits 2 of our own domain use cases. One is where one of our controllers, our IoT devices in the field, has been offline for a stretch. And instead of sending the data points for just one period, one interval, it will send the data points for a sequence of intervals. The other use case is where we're migrating data from Postgres to Cassandra to phase in Cassandra, and we want to do what we call a bulk import. At the component level, it makes sense for us to expose an API that can write not an unlimited number of readings, but a large number of readings as a single logical write. So I went about naively implementing these sort of bulk writes, employing our time-to-bucket mapper and bucket types to break up the batches by partition or by entire table. So here's what I first encountered when I did that. Okay, so I proceeded to add in another layer of batching to make each batch max out at 65,535 statements. And then on the server side Cassandra logs, I started seeing warnings like this. What confused me at first was, look at these two numbers. Without an indication of 65,536 what, I assumed that was returning to the number of statements. So how could there be over 5 million statements in a single batch? Eventually, I realized that this error message was referring to the number of bytes, not the number of statements. So eventually, through a bit of trial and error, I managed to right-size our payloads for the different tables, 500 rows for a live feed write and 275 rows for a bulk import. And even if we have the occasional warning that a batch is over 64K, well, it's occasional and not by much. An addendum, we eventually arrived at making the batch size configurable, and that in itself provides another form of throttling. Smaller batch size equals slower write. Let me spell out a distinction that I've been implying. We're talking about how the component level logical write exposed by the API, what constitutes the unit of work gets chopped up so that the data can be inserted into different tables. There's single insert per table. Here I'm talking about a single logical write consisting of one reading or measurement that leads to inserts into potentially multiple denormalized tables, but only one row being inserted into each table. There's single batch per table. Here I'm talking about a single logical write with multiple entries, which leads to multiple batch inserts going out across different tables, but each table's inserts are small enough that they can be confined to one batch insert, and that's to be distinguished from multiple batches per table. I've been giving extra attention to this last case, and it's a very powerful capability, but it does require extra attention. It would be much easier to implement batching if you were guaranteed that there was only one batch going to each table. In fact, though, with the way we are bucketing, it's hard to avoid having multiple batches per table, considering that the caller shouldn't be concerned where one batch ends, where one bucket ends, and the next bucket begins. So the real leap in complexity is going not from single batch per table to multiple batches per table, but just from single insert per table to batching. That's a complexity burden we're willing to bear, though, considering that instead of sending out 275 statements or 500 statements, depending on the type of write, we need only send out one. What I found myself having to do was to take all the input DTOs and sort them such that the cumulative tables were being batched and inserted in ascending order, and the latest tables were being batched and inserted in descending order. That ordering was both between batches and within batches. I had to do this to make the batch inserts perform more reliably, and when you think about the way the data gets written ultimately to the SS tables, I suppose that makes sense, although I arrived at the sorting through observation rather than as a conceptual exercise. With these bulk imports or bulk writes, yes, we can write a huge amount of data in a single logical write call thanks to our multi-batch support. Just keep upping the memory on the client, but just because you can do something doesn't necessarily mean you want to. So that brings us to the idea of right-sizing the component level write unit of work. Remember, our schema is idempotent. Our write unit of work doesn't have to be all or nothing in terms of whether anything gets persisted. However, the write itself is all or nothing. If one insert in the logical write fails, the whole write fails, which brings us to fail-fast failure handling. Remember, our write path keeps track of some very limited state per unit of work. And if at any point that state indicates a failure anywhere, the different writers are able to short-circuit themselves and preempt their next request to the server side, but lazily in their own time without preempting any work they've already done. This way, we're reducing the load on the cluster when there's already something going forward, and we're writing less data that's going to have to be rewritten anyway. With our current implementation, it's the responsibility of the caller to retry. So for our bulk import feature, the question becomes, what's the right size to reduce the chance of retries and to make the retries less onerous? And I should add that we have something called a duplicate bulk import barrier. With our bulk import feature, prior to following through with the inserts, the implementation does a check for the most obvious case where we can be certain that the data in question was already imported. And if it was, the implementation skips the bulk import and merely writes to an audit table the fact that the bulk import was skipped. Having gone through all this, we arrived at a bulk import size somewhat arbitrarily. Rather than import all the interval data for all time for a channel, we break it up and import it 1 month at a time, and that has worked fine for us. Here we get to another element of complexity that emerged from having to support multi-batch writes. Let me read from the message where I made the associated commit. Quote, for a given table, the series of inserts taxes Cassandra a lot less if we're able to guarantee that for a given table variation, not only are the batches inserted in order, ascending for cumulative tables, descending for latest tables, but that the ordered batches are serialized for that table variation such that the insert for one batch isn't requested until the preceding batch has completed according to its Guava listenable future callbacks being called, end quote. So you wind up with a workflow like this. For lack of a better term, this is a technique I called pseudo-transactions. Within a given table variations, the batch inserts have to be serialized. Otherwise, everything is going off in parallel, including between the different table variations. This is a special case of serialized execution rather than parallel execution. I think the simpler and more broadly useful application of this technique is at the API level, where a component level write call might have a dependency on the completion of a prior component level write call. That presumes a block on callbacks contract or its equivalent. And in fact, that's how we do the bulk imports. You can't write the next month until the prior month completes. Between this serialization of queries and the conditional chaining of queries with Guava's async function, you can do all sorts of nesting and composition of queries to create a whole acyclic graph or hierarchy of queries. And of course, there's a price to be paid in execution complexity for doing this. Only do so if you need to, but still, it's better than executing synchronously. I want to touch on metrics and monitoring a little bit. Earlier I mentioned session get state. You could take what that's showing and expose it using JMX. And then the driver exposes various metrics through this class metrics, which is geared to feed inputs into the code-to-hell metrics library. So you could feed the driver's metrics into JMX or wherever you have metrics pointed. But then what about the write implementation itself? This is where we can leverage the ingestion state and completion state types. And there you see some detailed metrics for a root completion state. We have yet to do this, but it would be useful for us to capture the trend lines on the different things being measured by these types and then expose them as JMX mbeans. We have a Datadog subscription we could take advantage of. We're already logging these states, though not necessarily at a high enough level that they're showing up in the logs. But suppose one of the metrics of a completion state exceeds a certain safe level. It would be easy enough for us to log the completion state at warn level whenever that happens, and then in our system that log will eventually show up in Splunk. You see our Cassandra persistence component can capture all sorts of information about how the write path is working and send that to JMX for the logs. By the same token, there's nothing stopping the application from taking what is gleaned about saving to the Cassandra tables and saving that information to its own Cassandra tables. So that's what we're doing with our bulk import functionality. On every bulk import call, if there's anything to be written, if the bulk import isn't being skipped, the first two tables are written to prior to embarking on the write path proper. And then, regardless of whether the first two tables were written to, regardless of whether there was anything to write or the write succeeded, the last table, bulk import audit exit, is written to at the end of the call. Every row in either of the first two tables will have a corresponding row in each other, and in the bulk import audit exit table, not every row and exit will have a corresponding row in the other two tables. Let me show the schema for the exit table. Note the two columns skipped and skipped reason. They get written to when the so-called duplicate bulk import barrier says the data was already imported. The failed and failed reason columns are for when an exception gets thrown in the course of the attempted write. So this becomes a record of what failures are cropping up, so long as you can look them up by the partition key, which is channel UUID. The duplicate bulk import barrier then distinguishes between skipped and failed to determine whether to let an import go through. Now, our bulk import call is a good fit for auditing every call because it's a sizable piece of work. But what about our live feed writes, where typically just a single measurement is coming in? It would be extreme overkill to write to an audit table every time one of these calls is made. Instead, what we could do, which we're not doing yet, is to aggregate the regular write calls and then periodically save the totals, the average, the min, the max to an audit table. This would require accumulating some additional state, and it could be a good fit for some library with a windowing function. Spark streaming, I don't know. Okay, all this while I've been building up to what I consider the most important slide in the presentation. Component integration testing. What do I mean by component integration testing? I mean automated tests, JUnit, TestNG, whatever, that are exercising the Cassandra persistence project against a real live Cassandra cluster. For our write path, these tests are inserting data into Cassandra and then verifying the result by querying Cassandra for the data and making sure that every last column in every last row in every table is what it should be. And these are tests that should be able to run on a local developer machine or on a CI server. We have a few options as to what that real life cluster should be. Some of this I'm sure is review for some of you. A local or remote vanilla install. This is what we're currently doing. On a developer machine, we've installed DataStax Enterprise, which we're controlling manually through bash scripts. The CI server is pointing at a remote DSE install. One downside to this approach is that, at least on a developer install, you're confined to a single node cluster. But there's nothing stopping you from having the CI server point at its own dedicated multi-node cluster. Cassandra Cluster Manager. This is a set of Python scripts to create and manage local Cassandra clusters. So it's a nice way to stand up a multi-node cluster on a developer machine. Cassandra Unit. This is a Java wrapper around an embedded version of Cassandra that gives an easy way to load schemas for testing. It's not quite a real Cassandra cluster. Here I'm talking about using something like Docker or Vagrant to stand up a multi-node cluster on a developer machine. The question then becomes, how much of what you're integration testing is really specific to a multi-node cluster, not to mention how big a multi-node cluster would you want? About our integration test contract. For all our existing tests, we're looking to start from a clean slate. For our write tests, we're starting from an empty database. For our read tests, we're starting from a well-defined set of data existing in the database. So our read tests are implicitly write tests. Whatever the Cassandra cluster is that the integration tests point at, we want to ensure that the schema migrations that define the keyspace only have to be run once. But then, as part of the test lifecycle, we ensure that before every single test of the write path, the entire schema gets truncated and any tables that would get dynamically created are dropped. So the database is in a state equivalent to dropping the keyspace and then running the migrations without having to do all that, although maybe it's just as well that we did do all that. Smoke test replays. This is not so much about the write path, but it's worth mentioning. We have the ability to point sort of an ad hoc integration test at one of our live environments, suck in the data for a given channel, and save that to a text file. And then that text file can be used as the input to another integration test that will replay the writes exactly as they were made in the live environment. And then the test itself would be to read that data. I look at this as something of a smoke test, but it gives us the ability to isolate issues that we might see in live environments. It should be apparent now what these component integration tests are not. They're not load tests or stress tests or performance tests. Those sort of tests are needed in addition. However, we are effectively using these integration tests to establish a very minimal functional baseline for a Cassandra cluster. For example, if the cluster can't handle the importing of 2 years' worth of one channel's data 1 month at a time with no other traffic to contend with, then that's a clear indication that the cluster doesn't pass muster. And finally, here's where our integration tests really fit in the big picture. There are all sorts of ways that we could improve our implementation. I've talked about a few, and I'll get into some more next. But you know how you might be in a meeting with your colleagues and you're debating, I think that would be much better if we did things this way. No, I think that would be a disaster. Having a strong integration test regime can give some immediate tangible feedback as to whether a change works, whether it breaks existing behavior, and, if only at a sandbox level, how it performs. Our write path has to send out all these asynchronous queries at once to insert one logical piece of data because our schema is highly denormalized, which is not so unusual for Cassandra. To reduce this need to denormalize to multiple tables, Cassandra 3.0 introduced materialized views. From this blog post, quote, materialized views handle automated server-side denormalization, removing the need for client-side handling of this denormalization and ensuring eventual consistency between the base and view data, end quote. When I first gave this talk, I was going to say this is not an option for us at this time because we're committed to DataStax Enterprise and DSE is not up to Cassandra 3.0. And then 2 days prior came the announcement of DSE 5.0, which does support Cassandra 3.0. A materialized view works if it's just a different sorting of the same data. It would probably work to collapse a few of our denormalized tables. For most of our tables, though, it wouldn't because they use fundamentally different bucketing granularities or because the buckets might be used as partition keys in one table and as part of the table name in other tables. But beyond that, materialized views would also force us to answer the question which table is the real table and which is just the materialized view. This may not be relevant until we decide we no longer need the main table and we want the view to stand on its own. So are materialized views a good thing? In the broader sense, yes, but like so many good things in Cassandra, they can be a bad thing. I think one of the mottos of Cassandra should be, there's no such thing as a free lunch. With Cassandra, you're making very deliberate, fine-grained decisions and trade-offs to make your database table scale and to make certain queries work and other queries not work. Like everything else, materialized views are not free. For every materialized view you write to, when you write to the main table, you're adding to what is effectively a transaction and making the insert more expensive. You could argue that if you don't need the strong consistency between the table and the view, the more Cassandra thing to do would be to write separately to two tables. The obvious trade-off there is more code, though not in your integration test. Your integration test is still going to have to check for the second table, whether it literally is a table or a materialized view. I want to touch on some higher level write abstractions. I mentioned this earlier. The DataStax Spark Cassandra connector is built on top of the DataStax Java Driver. So you can just take an RDD or a data frame and call save to Cassandra. If you're doing a Spark with Scala, this is clearly the way to go. If you're doing Spark with Java, there is an add-on Java driver, Spark Cassandra Connector Java. Phantom is a Scala DSL on top of the DataStax Java driver that supports the reactive streams spec. So it's a natural fit if you're working with Scala, and better yet, if you're looking to tap into reactive streams. After giving this talk, I received word that, at least as of a few months ago, the Phantom implementation was calling the DataStax Java driver synchronously. As explained earlier, this would be a violation of Cassandra client best practices, and it would be antithetical to reactive streams and to Scala principles. My guidance would be to examine the source, starting by searching for calls to session execute and session execute async. For my own sake, I'd go so far as to go back over the commit history and see if there had been widespread past use of session execute. Such use would throw into question the author's credibility, in my opinion. And finally, I want to touch on some lower level improvements that we could make or you could make. You might want to take a Guava listenable feature and convert it into a Java 8 completable feature. Why? Let me quote a colleague of mine who's a Scala aficionado. Quote, "You wouldn't have four comprehensions, pattern matching, and other Scala niceties, but then compose a similar to flat map and completable future apparently as a richer set of composition functions than listenable future," end quote. I happen to think listenable future is highly composable, although I can see how there can be less type bloat with completable future, and I can see how completable future can be an entry point for the more functional style programming Java 8 affords with its Lambda support. So how? Here's a perfunctory solution I came up with. You'd instantiate the custom completable feature, and then you can see I'm taking the completable feature I created and I'm binding its complete method to the future callbacks on success method and its complete exceptionally to the future callbacks on failure. Next, you might want to take a Guava listenable feature and convert it to a Scala feature. Why? Well, if you want to work in idiomatic Scala outside of Spark. And how? This snippet of code is adapted from the Akka Persistence Cassandra project, which is another higher level abstraction around the DataStax Java Driver. This next snippet is taken straight from the source for Logom, Lightbend's orchestration tool. It's the object Cassandra session impl. Compared to the previous example, the author describes it as making the conversion, quote, less magic, end quote. And here's how it might be called. Another potential improvement is to integrate with reactive streams. There's the reactive streams initiative and specification, which is based on the reactive manifesto. So you have libraries like RxJava and Akka streams and Vertex that implement reactive streams. And Java 9 is supposed to have a flow class that implements the standard. The spec is JEP 266. The idea would be to take our Cassandra write component that directly consumes the DataStax Java driver and make that work with reactive streams. So this goes back to the last component level contract I was talking about, stream and consumer contract. In fact, our bulk import application as it exists now is working with Akka streams. The difference is that the Cassandra write component is doing nothing on its end to integrate with Akka streams. The streaming application is just setting aside a pool of Akka dispatchers that call the component synchronously as if it were an external service. And finally, speaking of Akka, it would be interesting to try to take the asynchronous write workflow and delegate it to a thoroughly non-blocking Akka actor model. I don't know how this would be accomplished or if it would even be worth doing. I'm going to guess, though, that the aforementioned Lightbend source might give some insights into this.
Foundation gifts appear to be Donald Trump's gifts.
Okay, the title of this talk is Getting to a No Compromises Cassandra Write Path. So what do I really mean by no compromises? Consider that Cassandra is all about compromises. Think about CAP theorem, where you have to pick 2 out of the 3. Think about how Cassandra is not so much about eventual consistency as it is about tunable consistency. How it's about deciding you'll make this particular query go fast, but that other query, you're good with letting that other one go slow in an analytics cluster. As I said, Cassandra is all about recognizing there's no such thing as a free lunch. So this might sound like a bit of a cop-out, but I would argue that getting to a no compromises Cassandra write path is all about picking your battles, about making the right compromises. This means maximizing the parallelism of your implementation, but within the bounds of recognizing when you need to use lightweight transactions or to serialize certain writes. This means recognizing that your writes can overload the cluster, and there's a continuum of ways you can deal with this reality without having to resort to adding more nodes ad infinitum. This means making implementation choices or interface choices which may not be ideal but which meet your requirements. But you have the integration tests in place so that you can evolve towards better choices in an agile way. This last item gets back to broader best practices that are not specific to Cassandra. And there you have it. Thank you.